Hello guys, welcome back to Maison African Motives. Still working on mathematics N5, working on our revisions. That is, we are going to be talking about the rates of change, which is the applications of our derivatives. So in this case, you just need to know the basics of your derivatives. All right. So before we talk about these questions that we have, we've got a lot of questions that we are going to consider. We just want to understand what is it that we are talking about if we are referring to the rates of change. Take an example or a consideration that we have in terms of velocity. If we are talking about velocity, we say velocity is the change in displacement. That is the change in displacement with respect to time. So the change in displacement, we are talking about displacement changing. That is the displacement changing in this case, and also the time changing. So whenever we are talking about the rate of change, it must be a change of something over a change of time. We are talking about referring to time. So whenever we're talking about the rates of change, it must be with respect to time, with respect to time, and that time given in seconds or whatever that you be given for particular question. But basically, your time is supposed to be in seconds. So like I was saying that the velocity is the change of displacement over the change of time. Now let us put this in our rates of change, the way that we are supposed to have in our derivative. Given an expression for displacement that is given as S is equal to A t cubed plus bt squared plus ct plus d, whereby t is representing time in this case. This is t. This t is representing time in seconds, and s is the displacement. It follows that from this concept we can obtain the velocity, since we said is the change in this displacement over the change in time. So this can be given as, in terms of the derivative, that is the s dt. That is the change in velocity over the change in time. That is the derivative of s, which is our displacement. Remember, s here is our displacement, and t is representing time. So the change in displacement over the change in time gives us velocity, which is measured in meters per square second in this case. All right, that is from this displacement, we can obtain an expression for what? For the velocity, which is the same thing that can happen with acceleration. We know that acceleration is the change in velocity over the change in time. So that means is the derivative of velocity with respect to time, which is measured in meters per square second in this case. So if we check what is happening with acceleration, we are saying it is the change in velocity over the change in time. That is the derivative of velocity with respect to time, meaning to say whatever that you got from velocity, you are going to differentiate. We obtained velocity by differentiating displacement with respect to time. This is what is representing velocity. Now we are saying acceleration is the derivative of velocity, this part here. So what does it mean? It simply means acceleration can be taken as the second derivative of the displacement, because we did this part and we are now differentiating again. So it can be taken as the second derivative of displacement with respect to time. So that is how you can also obtain the acceleration. It's a second derivative of the displacement. But from velocity, you just differentiate your velocity, direct dv dt, you obtain an expression for acceleration that is in terms of t. So meaning to say you can find whatever that you want from there. All right, so this is about velocity, acceleration from displacement. We also have this rate of change considered. Let us say we've got a normal shape in this case, like mostly for solids. If we are given a solid shape in this case, let us refer to a cylinder in this case. All right, this is our cylinder, where we know that our cylinder, it has a height, perpendicular height, and a radius of r. All right, so from this point to this point, let's say this is where we have our radius r. Considering the volume of this cylinder, we know that the volume of a cylinder can be given as the base area times height, which is pi r squared h. This volume can be written, as we can see, in terms of two variables. We've got the radius, we've got the height, which affects this volume, where pi is a constant. This pi is a constant. So meaning to say, what can affect this volume of a solid, which is the cylinder? It can be the radius or it can be the height. If we change the height, the volume is going to change. If we change the radius, the volume is going to change. But pi is a constant, so this value is not going to change. It's a fixed value. So now, what happens is that we can be asked a condition whereby we have a rate of change. Let's say we have got a rate of change in this case of volume. Meaning to say, the moment we talk about the rate of change, it must be with respect to time. It must be with respect to time in this case. So the rate of change of volume with respect to time is going to depend from these two that we have, which is the radius and the height, like I was saying before. So if we are to write this in terms of height, it follows that dv dt, that is the rate of change of volume with respect to time, it is going to be equal to, take note what we need here. We are saying, let's say we are talking about in terms of the radius. So it is going to be the derivative of the volume with respect to the radius, the one that you are considering. Take note, the volume with respect to the radius. Then we have the derivative of that radius with respect to time, like this. So this is going to be an expression for the derivative of volume with respect to time. And for exam purpose, what you need here is to have dv dt. So like this dv dr, if you check here, if you multiply, if you consider this, we are remaining with the dv dt. If you do not obtain something like this to obtain back your dv dt, it means this expression is wrong, whereby maybe you might end up like dr dv times dv over dt like this. If you cancel this, it is giving dr dt, not dv dt. So it means on that condition, you'll be having a wrong formula. So check your formula to see that if these two cancels, are we going to obtain dv dt, the one that we have here? If you're obtaining that, then your formula is correct, whereby this is the derivative of v with respect to the radius, r with respect to time. The same concept, if we were to talk in terms of the height, which is h in this case, it means the rate of change of volume was going to be dv dt. This is the rate of change of volume with respect to time, which was going to be equal to, remember we are talking about height, so it's going to be dv dh, which is with respect to the height, times, we consider the height now in terms of t, so it's going to be dh dt. So that is the condition there, whereby dh and dh here, they cancel. If they cancel, what do we remain with? We remain with the dv dt, which is dv dt that we see here. So that is the proper formula that we can have. So it depends with the formula, or it depends with the solid that you're given. I'm not going to focus with all, we shall see from our examples. Maybe we are given a cone. In this case, we might be given a cone. Remember this, you are just supposed to know each and every concept about the shape that you're given. Remember, for a cone, you'll be given a consideration whereby you have got the perpendicular height and the radius again, whereby we are saying the volume of a cone is given as a third pi r squared h, a third pi r squared h, which is the same as this part. Our volume can be written, it's affected by the radius and also affected by the height. So meaning to say we can have the rate of change of volume with respect to time from the same formula, which is when you are talking about the height, about the radius, we can have the rate of change of volume with respect to time from this same formula if you are referring in terms of the height, because we have the same concept here. We have got r, we have got h, we have got r, we have got h. So this one is going to use the same concept. So like I said, it depends with what you are given. Sometimes you might refer to a rectangular prism, in this case, whereby we know that a rectangular prism, its volume is given by the formula LBH in this case, that is length times breadth times the perpendicular height. So our volume can be in terms of the length, in terms of the breadth, in terms of the height. So it depends with information that you're given. If we are to write in terms of the length, it means our derivative of volume, the rate of change of volume with respect to time, it is going to be the volume with respect to the length in this case. That is times the length now with respect to what? With respect to time. So if we can have this, you can now find whatever that you want. You can manipulate this formula into whatever that you want. And also the units that you are going to have, since this is the change of volume with respect to time, it means our units, depending if you are given your units in centimeters, it is going to be cubic centimeters per second. If they are just units, then you shall have cubic units per second or per given time. So it's like the cubic unit per given time. All right. If it is cubic meters, if it is time in meter in minutes, it's going to depend with the information. So these are the basics that you need to understand when you are talking about the rates of change. Talking about this part of displacement and velocity, acceleration, and this part of the rate of change of volume. All right, so let us check our questions. Like I said, also you need to know the basics of your derivatives, because some other part you need to apply the normal derivative, which is not even part of rates of change, but you need to know how to differentiate specific derivatives that you be given there. Like for this question that you're given, we are given the relative displacement, take note, in meters of a particle at a time t in seconds. So meaning to say here we are given displacement in meters and our time in seconds is defined by the function. So this is the function that is representing what? Displacement, the one that I was using last time as S is equal to AT cubed and so on and so on. Now they wrote this in terms of what? In terms of FT like this. What is the acceleration of the particle at 3,5 seconds? Acceleration, remember what I said, guys. If you are given displacement, it means you can find velocity, which is the first derivative of S, which was the S dt. So in terms of a function like this, if you're given in terms of f of t, your velocity is the first derivative with respect to t, which is in meters per second. Acceleration is going to be the derivative of your velocity, the velocity that you're going to obtain. That is your what? Your acceleration, or simply the second derivative with respect to t, this one that you are given, the second derivative. That is what you can have for acceleration. So meaning to say acceleration, you have to find the second derivative of the expression that is representing displacement. But if you are given velocity, let's say they gave us an expression for velocity like this, our velocity is equal to 2t like this. Then from there, you're asked to find acceleration. Your acceleration is simply going to be the derivative of velocity, because you already have the velocity. You simply differentiate that, which is going to be 2 meters per square second. But if you are given an expression of displacement, you have to differentiate that expression twice. That is to obtain what? Your acceleration. All right, so this is what you are going to have in this case. So we are going to find our acceleration from the second derivative of this function with respect to t. So that means all we need is to differentiate. Given our f of t in this case, all right, given our f of t, which is given as 4t squared ln t. So now, like I was saying, you need to know your basics, guys, of your derivatives. How do you differentiate this? Because to find the second derivative, you must find the first derivative with respect to t, which we can check here. This is a product, okay? So we've got a product there where we've got our u and our v. So remember from our product rule that the derivative of a product is going to be u, the first derivative of v, plus v, the first derivative of u. So that means here we are going to take our v as it is, u as it is here, u, which is 4t squared by the first derivative of v. How do you differentiate ln? Remember, ln is 1 over the first derivative of this function, which is the first derivative, sorry, of this function over f of that function, all right? So it's the first derivative of this, which is 1 over this function that we are given, which is t. So that is going to be 1 over t in this case, okay? Then we move on, plus v, our v, we are going to take our v as it is in this case, which is our v, it's ln t. So we're going to add ln of t, okay? So that is ln t in this case by the first derivative of u. So here, remember, this is a just normal algebraic part. Drop the exponent to multiply for, it is going to be 8t. We subtract a 1 here, so that will be a 1 like that, okay? So it's just going to remain as a 1, which is 8t. So you can just simplify before we proceed with finding the second derivative here. So let us just simplify where we can simplify properly. Like this is a product, so this is same as over 1. So t into t squared is going to be t. So we are going to remain here with 4t plus ln t times 8t is same as 8t ln t, like this, meaning to say these two are being multiplied together. All right, from here, we're just rewriting in a normal way. Now we are going to find the second derivative with respect to t, which is the expression for what? For acceleration now. So the second derivative, let's see what we have. This part here, we can just differentiate as it is 4t. It's a linear part, so we're just going to take this 4. So we are going to obtain 4 plus, if we check this part here, we have got a product again. We've got 8t times ln t, just like this previous part. So we are going to apply our formula, which states that we are going to take u. So this is our u and this is our v. So we have got u in this case, which is our u, it's 8t. So we are going to obtain 8t multiplied to the first derivative of v. And the first derivative of v, we've got ln t, which we differentiated it before. We got 1 over t. So this is a repetition on this part, plus in this case, our v, which is ln t. So we are going to obtain ln t multiplied to the first derivative of u. So our u is 8t. So the first derivative of 8t is going to give us 8 in this case. All right. So this is our expression, but we can just simplify further so that we can work with the simplified part here. So this 8, this t and this t can cancel since this is over 1. So we've got 4 plus 8, which is going to give us 12 from our calculator, plus here I've got ln t times 8. This is same as 1, so you can multiply 1 and 8 here, which is going to give us 8 ln t. All right, so this is what we are going to have at the end. So guys, this is an expression for acceleration. This whole part here is representing our acceleration. So meaning to say at the end, we are saying our acceleration is equal to, in terms of our derivative that we got, it is equal to 12 plus 8 ln t. This is the expression where we are going to obtain the exact value of the acceleration if we are given the t representing our time, and we have this t as our time, which is 3,5. So we are going to substitute now to say our acceleration is going to be 12 plus 8 ln of t, whereby we are given our t as 3,5 seconds. So this is going to give us our acceleration. So take note about this part that we are given. So it simply means that in place of t, you substitute the value of 3,5 that you're given. All right, so from your calculator, you're going to obtain something like 22,022 in meters per square second, which you can also write like meters per square second like this. All right, so that is how we could have obtained our acceleration when the time is 3,5 from displacement. Acceleration is the second derivative if you are given what? If you are given displacement. If you are given velocity, you simply differentiate your velocity as it is. If this question was for us to calculate the velocity, velocity is simply the first derivative of displacement here, which means to say our velocity was simply going to be what? Our velocity in this case was going to be taken as the first derivative with respect to t, meaning to say when we differentiated first here, when we differentiated first on this part, this is our first derivative, this one. This is the expression that represents the velocity. So if the question was asking you to calculate the velocity, this is the part that you're going to use. Okay, so in terms of f of this expression, the first derivative is velocity. The second derivative now, that is the expression for what? For acceleration. That is the expression for acceleration. So that is what you simply need to understand, whereby f of t is the one that is representing what? Displacement. So your f of t is your displacement that you are given. So that is how we play around with this. If you can understand this, you are done. Displacement, first derivative of that, it's velocity. Second derivative is acceleration. So you can now find whatever by substituting the value of t that you are given here. All right, let us check another part of our question here. All right, so let me do it like this. We also have a question again that is related or to this part or the second part. We shall talk about this later on, but let's start with the 3.2 that we are given there. So on 3.2, we are given here, let me take it down. So a water tank has a shape. All right, you can just increase, sorry for that. Okay, this is what we have here. So we have got a water tank as a shape of an inverted circular cone. We are now back to that part that I was talking about, whereby you need to know your shapes. So this is a circular cone of S radius, 2 meters, and a height of 4 meters. So meaning to say we have got something like this here, a cone. This is what you have on your indication. From this cone, we've got its perpendicular height here, which is given, and also the radius. So this is your radius, this is your perpendicular height. So we are given that the radius of this cone is 2 centimeters and the height of the cone is 4 centimeters. Then the question is, if water is being pumped into the tank at a rate of 2 cubic meters per minute. So take note here, we're talking about cubic. Okay, this is meters. Where am I getting the centimeters? This is meters. Now, I'm surprised to say, why is the information changing? This is 2 meters. This is 4 meters. So they are saying the water is being pumped at this rate. We're talking about the rate, which is, what are these units? It's cubic meters, meaning to say we are talking about volume here per minute, which is per time. So we are given rate of change, volume per time. The moment we talk about volume per time like this, volume over time, meaning to say we are given dV dt, that is volume over time, dV dt. So we are given the rate of volume with respect to time, which is 2 cubic meters per minute. Remember what I explained before about volume. I said the units for volume is cubic meters, cubic unit per given time. If we check here, what we explained about the volume, all right? You still remember here what I was expressing, that the rate of change of volume with respect to time is cubic units per given time, which can be cubic second, cubic centimeters per second. It can be cubic meters per minute, as long as it's the cubic units for volume as per time. That is how you know that you are given what? The rate of change of volume there. All right, so this is your volume, okay? Take note about the question now. The question is now, find the rate at which the water level is rising. Take note. The water level is rising, meaning to say the water level as it is rising. Let us take note on our diagram. This is our water level. It is rising. It is going up. What is being affected if the water level is going up? What is affected is the height that is being affected, not the radius, like where the radius. We are talking about when it is rising up. So this is how this question is all about. They are asking us the rate of which this height is going to be affected with respect to time, because the question is, at which find the red. The moment I talk about this red, it's that part that is being affected. What is being affected is the height. So it's the derivative of height with respect to time. Remember, I said whenever you're talking about the rate of change, it's what is affected with respect to time. Volume with respect to time. So the height is the one that is affected when the water is rising up. So that is what? Height with respect to time. When the water is 3 meters deep, so we are given at a condition whereby we are going to substitute this, we are given that it must be 3 meters deep. So we are given that H is equal to 3 meters in this case. That is what we are given. 3 meters deep, we are talking about the height that is being deep, okay? Wide, that is, we are talking about the radius, okay? But deep, it's the height, okay? So the question is here. We are supposed to find the HDT. I'm not going to rush on this question. We are going to be slowly answering this. We want to find the HDT from this cone, and we are also given a hint of the volume. Yes, sometimes you might not be given this hint. You must also know how to use your formula, okay? And also we are given that the radius of water level is given as we are given the expression for the radius to say radius is equal to h over 2. All right, this is what was supposed to happen, guys. I explained it before from that formula. When you are talking about the change of volume with respect to time, it means it can be affected by two things from this formula. It can be affected by the radius, it can be affected by the height. But here we are talking about given a height. So we must be talking about the formula for the volume with respect to time when affected by the height. And I said when affected by that, it is going to be the derivative of volume with respect to that height that is affecting this volume times the derivative of the height with respect to time in this case. Remember those formulas that we listed when we had height and radius. So this was the proper formula that we're supposed to use, this formula. But as you can take note now, we have this part, dVdt, we are given. What we need here is to find dVdh, whereby we have volume with respect to h. But here we have got radius at the same time, so it was going to be difficult for us to find dVdh. All right, let me write it here. Let me take it up, okay? Remember what I'm saying here. I'm simply saying we are given that the volume of a cone is given as a third pi r squared h, and also we are given a condition that r is equal to h over 2 on this part here. R is equal to h over 2. Why are they giving us this condition? Because on this part that we have here, we are supposed to be calculating the derivative. This part we do not have. We are supposed to calculate this, the derivative of volume with respect to height. But on this expression, there is radius, there is also height. So it is difficult now for us to find this. So we are supposed to write this volume in terms of h. So we are going to just say rewrite. We are going to rewrite V in terms of h. If we were to find our volume in terms of radius, we're going to change this V and write it in terms of the radius, depending with what you're given. So to find our volume in terms of h, we are going to substitute the radius in terms of h, because we are given that our radius is what? It's h over 2. So it is going to be a third pi times the radius squared, our radius being h over 2. Remember, we want our answer in terms of h. So that's r squared, which is h over 2 squared times h. So this is going to give us a third pi, that's h to the exponent of 2, which is h squared over 2 to the exponent of 2, which is going to give us a 4 in this case times h. So this is same as over 1, this is same as over 1. So we multiply everything on top. So we are on top, we are going to obtain 1 times pi times h squared times h, which is going to be pi h cubed in this case over 3 times 4, which is going to be a 12. So writing, all right, that is going to give us a 12 in this case. So we've got pi h cubed over 12, which you can write even as 1 over 12 pi h cubed like this. It's just one in the same way. So what we just want here is to have an expression for volume in terms of the height, because we must have dV dH. And for us to have dV dH, we are supposed to have this volume in terms of the height only. That is what you're supposed to have here. So now knowing that our volume is equal to 1 over 12 pi h cubed, let us find our dV dH. So our dV dH, in this case, that is the derivative of volume with respect to h. Remember, here we can differentiate, we drop the exponent. So it is going to be 1 over 12 times 3, which is going to give you 1 over 4 pi. Remember, after this, you subtract a 1. So that is going to be 3 minus 1 there, which is going to be a 2. So that is going to be h squared. So this is the expression for dV dH, this one. This is the expression for dV dH. So with this expression, we now have this expression. What is left? It is to have dH dt. What is this dH dt? This is the one that we are asked to find here. Remember, our question is saying we are supposed to find the rate of at which the water level is rising, which I was saying is your what? Your dH dt. This is the one that you're supposed to calculate. So how are you going to have this? Since we have dV dt, we can just substitute now because we have everything here. So dV dt, we have our dV dt here, which is 2 cubic meters per minute, which is equal to dV dH. Our dV dH, the rate of change, the change of volume with respect to the height here is given as pi. That is 1 over 4 pi h squared. So we are going to substitute this part. All right. That is, we are going to substitute 1 over 4 pi h squared, in this case, times what we are supposed to calculate, which is our dH dt, this part that is remaining of dH dt. So that's an equation. What we need is to find the dH dt. All right. Why am I writing like dt, dt, dt? It's dH here, dH dt. So what you need is to find this dH dt. So what are you going to do? You can simply cross multiply or just divide here what we have to remove this fraction. You can multiply by 4 here, multiply by 4 here, so that will be 4 times 2, which is 8, is equal to, we are left with this one, it cancelled here, so we are left with the pi h squared. So we are going to divide by pi h squared. So this is going to remain as dH dt. Since it is under multiplication, we divide. So this is the expression for dH dt. So that means, therefore, we can find our exact value for dH dt. So therefore, from this part here, our dH dt, which is the change or the increase of height or the change in terms of height with respect to time, from this expression that we are given as 8 over pi h squared. This h is the height, not from the cone. Take note, not this height of the cone. It is the height that is affecting at that moment, because here they are saying here, find the rate at which the water level is rising when the water is 3 meters deep. So we want to know the change there when the water is 3 meters deep. That is the question. So meaning to say, we can now substitute this height into our question to find the exact change of what? Of volume in terms of this height. So that's 8 over pi times the height, which we said our height there was 3 meters being squared. All right, so that was going to give us the expression, given that our h is what? Given that our h is 3 meters, we're going to obtain 0.283. This is the change of height being measured in meters. So it is going to be in meters per our time. Remember, our time here is measured in minutes. So it is going to be meters per minute. So that is how we were supposed to end up with our expression for the increase in the height, in the change that is happening in terms of height. This is what you need to play around with. So guys, you need to just know these basics. Formulate your data from what you're given. Formulate the formula that you are supposed to work with from the change of volume that you are given. Manipulate your formula and see which part are you given. This part, you can obtain it because you can express a volume in terms of height. Find this part. Then you are left with this part, make it the subject, substitute the value of the height at the final stage. The height not of the cone, but the height that is affecting at that condition when the height is 3 meters deep, or when the tank is 3 meters deep at that particular moment. All right, so that was the first part of the applications. We shall see in another part. Let us see this one now. All right, the position function of a particle is given as S. So take note about that part. Is given the position of a function, which is we are talking about what? The displacement, where S is the displacement in meters and T is the time in seconds. So this expression that we are given for S is equal to T cubed. So we are given S is equal to T cubed minus 4,5 T squared minus 7T in this case. And we have a condition to work with at this moment that T must be greater than or equal to 0. We need only values that are greater than or equal to 0. So remember, I talked about this one. It's just a repetition here, where S is what is our displacement and T is representing the time. So the question is, now we are asked this part. When does the particle reach a velocity of 5 meters per second? When does it reach a velocity? Take note what we are given here, a velocity of 5 meters per second. When, meaning to say, what are we referring to when we are given when? We are referring to time in this case. The question is for us to calculate the time. Given that the velocity at that moment is equal to 5 meters per second, how are you going to calculate the time? Remember what I said, guys. The relationship that is there between displacement and velocity is that velocity is equal to ds dt, which is the first derivative. So by differentiating this part here, by just differentiating this part, we are obtaining an expression for velocity. So let us differentiate this. So our velocity is going to be ds dt. So we're going to differentiate this part. So drop your exponent. That's going to be 3t. Subtract 1. So that's 3t squared. We do the same here. Drop the exponent 2 times negative 4,5. That is going to be negative 90. Then here we've got a linear part, which is negative 7. This expression that we see here, guys, is representing velocity. This is the expression for velocity. The first derivative of displacement is your velocity. But now they want us to calculate the time, given that this same velocity that we have here, it is equal to 5. These two, they are equal. So it's an equation that you are formulating because you are given that your velocity is equal to 5. So the velocity of 5 and the velocity of this one, they're equal. So what does it mean? We are simply going to formulate an equation, which is 3t squared minus 9t minus 7 is equal to the velocity, this one, a numerical value. As this one is an expression for velocity, this one is the numerical value, which is the exact value for velocity. That is the difference that we have. So here we can try to solve 3t squared minus 9t. We can transpose 5 to this side, which is going to give us negative 7. Negative 5, which is negative 12, is this in this case is equal to 0. Since 3 is common here, we can divide. Since we are given an equation, we can divide each and every term by 3. In this case, that's going to be t squared minus 3 into this, that's going to be minus 3t. 3 into this, which is going to be negative 4, is equal to 0. So we can solve this equation as by factorization. You can use your quadratic formula, guys, whatever that you are good at. We have factors of negative 4 here, which gives us a negative 3 when added. So factors of negative 4, which will add up to negative 3. We have got negative 4 and 1. Okay, if we add up these two, they give us negative 3. If we multiply, we get negative 4. So we've got negative 4 and 1. So we've got t minus 4, t plus 1 equal to 0 in this case. So from these values, each bracket must be equal to 0. So t is going to be a 4. On the other hand, negative 4 is going to be a positive, or t is going to be positive 1. On the other hand, is going to be a negative. But let us take this consideration that we are given. They told us that our t is supposed to be greater than or equal to 0, and whatever condition that you have, your t is supposed to be greater than. So meaning to say, we need, if we are saying our values that are greater than or equal to 0, we are simply talking about positive values in this case. So your t is supposed to be positive. So in this case, we are supposed to take t as a positive. So therefore, our t at that moment was going to be 4 seconds in this case. All right. So this is how we play around this typical question. Take note, the first derivative of the expression that you obtain, this one, is representing your velocity. That is the first derivative of what? Of the displacement. The displacement. Okay. On item 2, 3.2, now they're asking, when is the acceleration 0? Another part again, when we're talking about time. But talking about what? Acceleration equal to 0. So again, we are back to that part again to say we are talking about acceleration. Remember what I said here. All right, so this is the condition 3.32. All right, so we are talking about finding time when the acceleration is equal to 0. So remember what I said from about the acceleration, that acceleration is the change of velocity over the change in time. If you are given from the displacement, acceleration is the second derivative of the displacement with respect to time. So already here we calculated our expression for velocity. This is the expression for velocity. So what do we simply need from this expression? We simply need to differentiate this. So acceleration is going to be dv dt. So we are going to differentiate 3 by 2, which is going to be 60 minus what? Minus 9. If you use the second derivative, you're going to obtain again, which is your second derivative with respect to t. So and the same thing, you find the first derivative. You find the first derivative of s, s with respect to t. You find the second one. You are going to obtain the same answer, which is 9 minus what? Which is 6 minus 9t. Now that we have the expression for acceleration, our question is, when is this acceleration equal to 0? When is it equal to 0? Meaning to say our acceleration is equal to 0. We can find the value of t by equating this to 6t minus 9, which is our expression for acceleration. It must be equal to the exact numerical value of our expression, which is 0. So we have formulated an equation where we can solve for t. So 6t is equal to transpose 9 to this other side. Negative 9 is going to be a positive 9. So to find t, simply divide by 6 both sides. We have our t in this case, which was going to give us 1.5 seconds. All right, so take note of your questions. This time, the question was asking the time when acceleration is 0. So you have to find an expression that is representing what? Acceleration. This is the expression for acceleration. This was the expression for velocity. This is the expression for displacement. You just need to know this part. From displacement, you find the derivative, you get velocity. The derivative of this velocity gives us acceleration, but take note of the conditions that you'll be given. When acceleration is 0 or when velocity is 0, you have to work from the given consideration for that particular question so that you obtain exactly answers that are expected. All right, then we've got another part again here. So let us check our questions. How are they given? So this time we are given, okay, let's see. That is question 3.2. We have got an airbag in this case is being pumped into a spherical ball. So take note, this was being pumped into a what? Spherical ball. We are talking about a sphere, whereby we are given the volume of a sphere. Sphere is just like a circular thing, okay? So we're given the volume of a sphere in this case, in such a way that its radius increases. Take note what is increasing. Take note what is increasing. The radius is increasing at a rate of per minute, meaning to say per time. That is the change of radius with respect to time. The radius per minute, which means per time. So we are given the rate of change of radius. This is what you are given. Use the information that you have. Now the question is, find the rate of change of its volume. Now we are talking about the rate of change of its volume. So the rate of change of the volume is with respect to time, definitely. So we do not know this. But what we know is this is going to be in cubic meters per what? Per minute. Remember, volume, cubic units per time. When at a condition, when the radius is 5 meters, at a condition where R is equal to 5 meters, find the rate of change of volume. We are back to the same particular question that we had before. With this information that we are given here, remember what I said. You have to find dv dt from the expression of a radius. So which formula is best to use that we are going to take from dv dt? So it must be the volume with respect to the radius because we are dealing with the radius. So it is going to be dv dr, okay? So we are going to have the volume with respect to the radius times what is affecting with respect to time, the radius with respect to time. Whereby I was saying these two, they must cancel so that we remain with the dv dt, which is same as this dv dt. If they do not cancel like this, it's wrong. Okay, so this is the one that we are supposed to calculate. We do not know this. This is the one that we are supposed to calculate. Okay, let's check dv dr. Do we have dv dr? This one we do not have, but we can calculate it since we are given volume and radius. We can find the dv dr there. So in this case, from your volume, since your volume is given as 4/3 pi r cubed, what is going to be our dv dr? So remember, we have just saved r as a variable. Pi, it's a constant, it's a number, so it does not affect. So you drop the exponent 4/3 times this 3, which is going to give us what? Which is going to give us 4. This one will cancel, so we're going to remain with 4 pi. Remember, subtract 1, so 3 minus 1, which is going to be a 3 in this case. So we are going, which is going to be a 2. So we're going to have 4 pi r squared. So we have dv dr in this case. This is our dv dr. We also have dr dt, the one that we're given from our information, we have it. So this one is just a substitution we calculated this. So meaning to say our dv dt was going to be equal to dv dr, which is our dv dr here, which is 4 pi r squared times dr dt, the derivative of the change of radius with respect to time, that one that we are given of 0.75. So this is the expression that we are supposed to obtain our volume, change of volume in cubic meters per minute. When the radius is 5 meters, we are given the radius at that moment that it's 5 meters. So we are going to substitute now our radius to find the exact value. So our dv dt is going to be 4 pi times the radius, which is 5 meters squared times 0.75. That's it. So this is how we play around with this question. So this one was going to give us 75 pi in cubic meters per minute. Remember, we're talking about volume, that's cubic meters per minute, or you can write it as a decimal, which was going to give us 235,619, which is in cubic meters per minute in this case. All right, so that was the play around of this question. I think this one was clear. That was the play around. This is how we simply play around with these typical questions. All you need is to understand how the information is given and the formula, especially that I was explaining for dv dt in this case, if we are dealing with dv dt. All right, now we've got another particular question with respect again to the change of this volume term. Here we are given a hint and even a diagram. All right, let us check what we're given. That was question 3.2. All right. A cylindrical tank filled with water, in this case, is a radius of 5 meters. So the radius here given on top, they're just saying here, the arrow here is pointing here. So this is 5 meters. And the height of 12 meters, which is this height, it is drained. So take note, we are draining. To drain is like we are reducing like there is a hole in this case, and the water is pouring out, is getting out. That is to drain. So that is what is given. So whenever you are doing this, it means you are subtracting. If this tank is full of water, we are going to end up with an empty tank, or we are going to check and see the water is at a certain level because you are draining the water. So meaning to say here, whenever we are talking about it's a decrease that is happening. So a decrease is always represented with a negative. So, all right, let us see what is happening. It is drained such that the depth, we're talking about the height there, all right? The depth of water decreases by, meaning to say the height with respect to time. That is what we are given. The depth, the height with respect is decreased by what? 0.3. So it's going to be a negative 0.3 meters per second. Since it is a decrease, it is going to carry what? A negative. The question now is, how fast is the water draining from the tank? How fast is the water draining? Meaning to say, we're talking about the volume of water draining. The volume of water draining. That is, we are talking about the V with respect to T in this case. How fast is this going to affect? Okay, so we are talking about dV dt, the volume with respect to what? With the volume with respect to the water, the volume of water with respect to time. How fast is the water? The water, we are talking about its volume with respect to time. The sketch is given, and we've got a hint here for the volume. We are given that the volume can be given. This is a volume of what? Of a cylinder, which is given as pi r squared h. All right, so this is what we have in this case. Okay, just this information, they are done. So they want us to calculate how fast, which is dv dt. Okay, remember what I was referring again. In order for us to find dv dt, we have to connect our formulas here. dv dt is going to be, we are given, what are we given? We are given in terms of height. This is what we have. We are talking this in terms of height. So meaning to say we are supposed to find the volume, the derivative of volume with respect to height. And that same height changing with respect to time, which is dh dt. So these two cancel. We remain with the dv dt, which is dv dt. Our formula must be like that, right? So if you check, this is what we want to calculate. We are not given this part. But are we given dv dh? dv dh means the derivative of volume with respect to h in this case. So on a condition like this, where you are not given a consideration, they know what's going to happen. H here, it's, okay, let me take it like this. I want you to understand before I explain this. If you are given y is equal to 2x like this, it's a linear expression, this one. The highest exponent here is a 1. How do you differentiate y with respect to x? Your answer, you don't even need to just say your answer is 2. The coefficient of x, that part that is affecting x, that is your derivative of y with respect to x, because this is a linear term. So this is the same h, the highest exponent of h here, it's a 1. So we are simply going to take what is multiplying our what? Our h. What is multiplying our h in this case is what? It's pi r squared. So that is the derivative of what? The derivative of v with respect to h is going to be what? Pi r squared. The part that, because it's a linear term, it's a linear. So you just take the coefficient. If you are given y is equal to 20x, the derivative of y with respect to x is going to be 20, because we are talking about a linear expression. So that is how we could have taken this part. All right, so we have our expressions here, which are enough in order for us to calculate the dv dt. If we are to take from our information, this is enough. Considering this part here, we are going to have our dv dt being equal to dv dh, the derivative of v with respect to height, we got pi r squared, times the derivative of h with respect to t, which is the rate of change of our height with respect, which is the one that we said it's a negative. So this one is going to be negative 0.3. All right. So the answer there being affected now, as we can check on this part, what is going to affect our answer? It is the height at that particular moment. The radius at that particular moment is the one that is going to affect our rate of change of the volume. And given a radius, in this case, we are going back now to the radius that we are given of what? our radius of 5 meters. So that was the consideration of this question. Be careful on this type of a question that we are having here. So we are going to have our volume decreasing. That is, we are going to have our volume as a negative. So it's pi times our radius, which is 5 squared, times the negative 0.3. So this was going to give us negative 15 over 2 pi, which is cubic meters per watt. Our volume here was given in what? Meters per second. So it is going to be cubic meters per second. You use the units that you are given. So thus, in this case, as a decimal, you're going to obtain negative 23,5625 in cubic meters per second. So what does the negative simply represent? It simply means that's a decrease. So that's a decrease in this case. That's all right. So that's the volume is decreasing. So our volume is decreasing in this case at 23.562 cubic meters per second. So once you are having this, once you write it is decreasing, there is no need for you now to write the negative on your answer. Once you write that, the volume is decreasing at. But if you leave a negative, it shows that your volume is what? It shows us that your volume is or the volume was decreasing in this case. All right, so that was the first part of our question here. Take note, 4 marks for that. So, but you just need to connect your formulas. As you can see, it's a matter of connection of formulas. All right, let us check the other part. Now on 3.3, we are given position. Okay, we are back again to the part of our like linear motion concept, whereby we are given the position. Particle is given by this equation. So this is what is representing our particle in this case, which by ST is measured in meter. What is measured in meter? We are talking about displacement here in meters. So this is our displacement. So ST is representing displacement and T in seconds. All right. So this is our displacement in meters and our time in seconds. So the question is, when does the particle reach the velocity? I think this one is similar to the other question that we did. All right. When does it reach this particular moment, particular velocity? So we say the velocity here is simply the first derivative of displacement. When you are asked when we are talking about the time at that particular moment. So we are going to have our ST in this case being equal to a third, or you can even just have it guys at once, or let me just rewrite a third T cubed minus half T squared minus 3T like this. So we are saying, when is it going to affect this? When it is 3 meters per second. What is 3 meters per second? That's our velocity. So they are saying when the velocity is 3 meters per second. If you check, we talked about this same type of a question direct as it is, but for the sake of revision, what are we going to do? We said velocity must be equal to the first derivative of what? Displacement with respect to time. So all we need is to find our derivative here with respect to time, drop the exponent, multiply a third, subtract 1. So we're going to have T squared minus 2 times a half. That is going to be 1. We subtract 1, so that will be a T. This one, we are back to that linear term. So we're just going to take the 3. So our answer there is going to be T squared minus T minus 3. So they are saying the velocity at that moment is 3 meters per second. And this is the expression for velocity, which is T squared minus T minus 3. So we are simply going to equate these two to say T squared minus T minus 3 must be equal to the velocity, the numerical value of that velocity that we are given. So now we can solve for T. T squared minus T transpose 3 to that side is going to be a negative. So that's negative 3, which is negative 6 is equal to 0. Do we have factors in this case? Because we are supposed to solve our equation. So we need factors of negative 6. That will give us what? A negative 1 in this case, since the coefficient of T squared here is 1. So simply need 2 brackets. That's T and T. So the factors of negative 6 is going to be negative 3 and 2, which gives us a negative 1. All right. So that's negative 3 plus 2. So equate to 0. 3 is going to be, T is going to be equal to 3 or t is going to be 2 to the other side is going to be a -2. So that is, we can have their values. So if you are given that t should be greater or equal to 0, we are going to take our t being 3. But in this case, we are not given. Just write the two answers as they are. That t is -3, -2, or our t is +3. Then when is the acceleration 0? When is our acceleration 0? Again, we have the same type of equation here. So we said for our acceleration to be equal to be, all right, our acceleration is 0. For us to have acceleration, we work with the velocity, whereby we are simply talking about the second derivative. So acceleration is simply the derivative of velocity in this case, which is simply means the second derivative with respect to s. This is our first derivative. So we are simply going to find the second derivative there. That is, we drop our exponent here, which is going to be 2t minus 1. Here we are dealing with the 1. And this is a constant, that's a 0 there. So this is the expression for our acceleration, this one. So from this expression of acceleration, the question is, when is it equal to 0? When is this acceleration equal to 0? So we are simply saying 2t minus 1 should be equal to what? Should be equal to 0, which is our acceleration. So that's 2t is equal to 1. Divide by 2 by 2, our t is going to be 0.5 seconds in this case, when the acceleration, when we are given a condition that our acceleration in this case is equal to what? Is equal to 0. All right, so as you can see, this is how they play around these questions. They actually try by all means to confuse you guys along this part. All right, so what you simply need is to work with more revisions, more question papers. Try by all means to work out as much as you can. But if there's any question or any challenging part, or any part that is still having confusion on this part, let us know in the comment section so that we can try by all means to work on that. Or if you have a question that is specific, let us know about that question. Not forgetting our members who are being part of this program, who are helping us a lot to produce these videos. Let us join the membership family so that we can spread this gospel of light to as many people as we can. But for now, guys, that's it from Maths on African Motives. Till we meet again.